Welcome back to part 2 of section 4.4. We're going to have another example of pretty much the exact same thing we just did. We're going to find points of inflection to discuss the concavity of this mess. Okay? So we have a graph, we have a function, and we want to find out where is this thing concave upward, where is this thing concave downward, and does it have any points of inflection? All right, so the process is the same as the last time. I need to find where the second derivative does not exist or where the second derivative is equal to 0, and those will be our candidates for our points of inflection. And then we'll take a look at the intervals surrounding those candidates and see whether it's concave upward or concave downward, see if change occurs at a point, and then determine whether that point then is a point of inflection being on the graph or not. All right, so first things first, I need to get some derivatives going on here. All right, so I'm going to rewrite this as 6 times x squared plus 3 to the negative 1, at least for my first derivative, just to make taking that first derivative easier. So f prime of x will then be, what is that going to be? Negative 6 times x squared plus 3 to the negative 2 times 2x, or what is that? Negative 12x over x squared plus 3 squared. There's my first derivative. Now I'll take the second derivative, f double prime of x. Let's see, second derivative. Looks like I'm going to have to use the quotient rule here. So the quotient rule says it's the denominator multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator divided by the denominator squared. Okay, I'm seeing a common factor of x squared plus 3 in all three terms, so I'll take that out and simplify. Oops, I don't want to use green. I use that for the first derivative. Let's use orange. Let's see, so that's going to give me then, let's see, I've got a negative 12 times an x squared plus 3 left in this first term, plus, let's see, negative makes it a positive, so plus 12 times 2 times 2, so 12 times 4 is 48, and I got an x squared over x squared plus 3 to the third. Factored one of them out of each of those three that are highlighted pink. Right? Let's see, clean that numerator up a little bit more. If we do this distribution right here, we're going to get 48x squared minus 12x squared, which will give me 36x squared minus 36 over x squared plus 3 squared. Right. So now that I've got my second derivative, now I'll find those candidates. Are there any candidates where the second derivative does not exist? Now, given that we've got a division problem here, there is the possibility that we could have a division by zero error, but I can't think of a value that when I plug it into that denominator, that when plugged into this denominator right here would give me a 0 downstairs. So I'm going to say that there are none of those. Are there any where the second derivative is equal to 0? All right. Now, given that this second derivative is a rational function, a fraction, the only way for a fraction to be equal to 0 is if the numerator is equal to 0. So I'm just going to take that numerator, set it equal to 0. 36x squared minus 36 is equal to 0. I'll factor. That's going to give me 36 times x squared minus 1 is equal to 0. So that means that x could be 1 or negative 1. So I have two candidates for points of inflection. So now I'm going to draw that number line and test intervals and all that business. Okay. So our number line, we have two candidates, a negative 1 and a positive 1. That gives me 3 intervals to test. Right. Interval number 1, I'll use -2. Okay? And so I need to find f double prime of -2. All right, so I'm lazy, so I want to point something out. That denominator will always be positive no matter what x is. Because no matter what ends up inside of those parentheses, it's squared. And so positive here plus more makes it more positive, squared makes it even more positive. So the sign of the second derivative is solely based on the numerator. When the numerator is positive, the second derivative is positive. When the numerator is negative, the second derivative is negative. Right? So f double prime of -2 is going to be something over a positive number. When I put a -2 into that numerator, -2 squared is 4. 4 times 36 minus 36 will also be positive. And so I'm looking at positive divided by positive. Remember, I don't really care what the value is. I just need to know whether it's positive or negative. So that means that on interval number 1, f double prime is positive. Okay. Now let's check interval number 2. And I'm going to be just as lazy here. I'm going to use 0. Okay? And so when I plug 0 into that thing, when I find f double prime, the second derivative at 0, I get -36 over 9, or a negative value, which means we are then less than 0. Okay? Interval number 3. I'm going to choose 2. Whoa, what's going on here? I'm going to choose 2. And I'm going to plug 2 into this. But remember, all that matters is the numerator. Okay? We don't have to worry about the value of the denominator. It's always positive. So in interval number 3, f double prime of 2 is going to give me something over positive. Let's see, 2 squared, 4. 4 times 36 minus 36 is, so it's positive, positive, positive again. Positive divided by a positive gives us a positive value. And so f double prime is greater than 0. Right? Now, seeing what I'm seeing here, what does that say about this and this? Right, so -1 to the left, concave up, to the right, concave down. +1 to the left, concave down, to the right, concave up. So it looks like we have changes in concavity. So now the last thing to do is to write this all up and make this look pretty. So where are we concave upwards? We're concave upwards when the second derivative is positive, so that's interval number 1. So -infinity to -1. We're also concave upward on interval number 3, so union with 1 to infinity. Where are we concave down? That's where the second derivative is negative, so that's interval number 2. So that's -1 to 1. And then the last thing is, do we have any of these? Any points of inflection? Well, concavity changes at -1. Concavity changes at +1, so we have potential there. It could be -1 comma something and +1 comma something. And how do I find those missing y values? Well, I have to take the -1 back up to the original function and the +1 back up to the original function. Right? So if I plug in a -1 in the original function, what is f of -1? Well, that's 6 divided by -1 squared plus 3. -1 squared is 1. 1 plus 3 is 4. 6 divided by 4 is 3/2. Okay. Now I'll do the same for +1. Okay. What is f of +1? Well, that's going to be 6 divided by 1 squared plus 3, which is also 3/2. And so I have determined points of inflection, as well as I have found the, what are those called? Oh yes, the points of inflection and the intervals of concavity. Okay, so I can find points of inflection, and I can discuss the concavity of a graph. Now, if you're wondering what this one looks like, that it has this behavior, here's a graph of the function. And you can see that over there at -1, comma f of negative 1, there's a point of inflection, as well as over at 1 comma f of 1, there's another point of inflection. And that to the left of that black point on the graph, we're concave upward. Between the black point and the red point, we're concave downward. And to the right of the red point, our graph is concave upwards. Gosh, I love Desmos. All right, let's take a look at another example. This one looks like it's going to be nastier. And the reason I'm saying that is just upon initial inspection, right? Upon initial inspection, it looks like I've got a couple of asymptotes. Look at that denominator. The denominator of this function is x squared minus 4. X squared minus 4 has two zeros, and x equals positive 2 and negative 2. So I'm betting that this thing is going to have some behavior where concavity might change, and we might not actually get a true inflection point. All right, so let's go ahead and get started then. Same question. Determine those points of inflection and discuss the concavity of. So we need that second derivative. So first derivative, f prime of x, quotient rule, denominator, multiplied by the derivative of the numerator, minus the numerator, multiplied by the derivative of the denominator, divided by the denominator, squared. Clean that up a little bit. Looks like we've got a 2x cubed minus 8x minus 2x cubed minus 2x over x squared minus 4 squared. All right. So distribute here. That's my 2x cubed. Distribute here. That's my negative 8x. Distributing here, that's going to be these two terms right there. Right? It looks like we have some cancellations that will occur and some combining of like terms. So we're looking at a negative 10x over an x squared minus 4 squared for our first derivative. But we need the second derivative. So now we'll do it again. F double prime of x, the second derivative. Denominator multiplied by the derivative of the numerator, minus the numerator, multiplied by the derivative of the denominator, over the denominator, squared. Right? I'm seeing a like term. Right? So I'll factor that out and see what's left. Let's see. When I factor that out in the first term, I'm going to be left with this negative 10 times an x squared minus 4, or a negative 10x squared plus 40. When I factor out the second term, I'm left with a negative of 2x and a 10, so that's what, 40x squared plus 40x squared over, just checking my math real quick, an x squared minus 4 cubed. Cleaning that up a little bit, it looks like we've got 30 x squared plus 40 over x squared minus 4 cubed for our second derivative. Okay. Now that we've got our second derivative, we're going to find out where it does not exist. It doesn't exist now because we're dividing here. We have to worry about division by 0, and so it will not exist when x is 2 or when x is negative 2, because those are zeros of the denominator. When will it be equal to 0? Well, given that it's a fraction, again, all we have to worry about is when that numerator is equal to 0, and so that'll be when, whoa, don't want that one either. I'll figure it out, third time's the charm. When 30x squared plus 40 is equal to 0. But let's look at that for a second. No matter what value you put in there for x, that's positive. And a positive number times 30 is still a positive number. And a positive number plus another positive number can never equal 0. So this will actually never happen. So it turns out we actually only have two values, two candidates that we have to worry about. So now I'll draw my number line and I'll test my intervals. There's -2, there's +2. That's going to give me 1, 2, 3 intervals to test. I'll test interval number 1 first. I'm going to use -3. Okay, and I'm going to put this into the second derivative. So what is the value of the second derivative at -3? Well, that's going to be 30 times -3 squared plus 40 over -3 squared minus 4 cubed. Now, just like earlier, we have something interesting going on here. No matter what number I put into that numerator is always going to be positive. So upstairs is always positive. What about the denominator? The denominator can change signs because it's being cubed. Right? Since the denominator is being cubed, it can change signs depending on what happens inside of those parentheses. So if those parentheses give us a positive value, then cubed will be positive. If the parentheses give us a negative value, then cubed will be negative. So let's look at what's happening here. I got a -3 squared, that's 9. 9 minus 4 is 5. 5 cubed is positive. Positive divided by positive means on that first interval, our second derivative is greater than 0. Now we'll check interval number 2. Right? Interval number 2. I'm going to use 0 because why not? What is f double prime of 0? Well, I know it's going to be positive over something. Downstairs is going to be 0 squared minus 4 cubed. That's negative downstairs, so it's a positive divided by a negative, which means on the second interval, our second derivative is negative. Okay? Interval number 3. I'm going to use 3. Okay? What is f double prime of 3? Well, I know the numerator is positive. Downstairs, I'm going to have 3 squared minus 4 cubed. But this is going to be 5 again downstairs, so that's going to be positive again. So our second derivative will be greater than 0. Right? So what does that mean about this and this? Now, you would be tempted to say that we have points of inflection at -2 because to the left it's concave up and to the right it's concave down. Or you'd be tempted to say that we have a point of inflection at +2 because to the left is concave down and to the right it is concave up. But actually, we don't have anything at -2 and +2. Because if you were to attempt to evaluate the original expression with either -2 or +2, what's going to occur in the denominator? Right? Downstairs, 2 squared minus 4 is 0, or -2 squared minus 4 is 0. We have some sort of discontinuity at -2 and at +2. And so while concavity does change at -2, and concavity does change at +2, they are not points of inflection. Right? So last thing we'll do is we'll wrap it up, make it look pretty, write everything out. So when is this graph concave upwards? Well, it's concave upwards on interval number 1, which starts at -infinity and stops at -2. It's also concave up on interval number 3, which starts at 2 and stops at infinity. Where is it concave down? Well, that would be interval number 2, which is from -2 to +2. And how about points of inflection? Well, we would say that there are none of those. Okay? The problem asks us to determine them. I determined there are none, so I'm going to write down none. So x squared plus 1 over x squared minus 4. So this is the graph of that function, the x squared plus 1 over x squared minus 4. You'll see that there are 3 distinct intervals, 2 concave up, the left and the right side as we're looking at it, 1 concave down. But there is no point of inflection because we have a vertical asymptote at -2, and we have another vertical asymptote at 2. Equals 2. All right. This brings us to the end of this video. Well, actually, yeah, the end of this video. Our next video, the third part, will be using the second derivative test. I'll see you all back here for part 3.